Let's talk about particle motion. What we see is that there's a clear relationship between our position s of t, our velocity v of t, and our acceleration a of t. In particular, what we notice is that the derivative of our position function will give us velocity, and if we take one more derivative, we'll end up with acceleration. Therefore, v of t, our velocity, would equal s prime, or the derivative of position, and our acceleration a of t would either be v prime, the derivative of velocity, or two derivatives of our position. So what we see is that differentiation can help us go from position to velocity to acceleration. Naturally, we'd ask ourselves, okay, how do I go from acceleration back up to either velocity or position? We see that with the help of integration, we can move from our acceleration function to our velocity function, and then if we take one more integration, we can go back to position. Note that with the integration, if we're not given an initial condition, our solution for the velocity function or the position function would be a general solution, which means we'd have a plus c. With the initial condition, we could actually solve for that plus c. Let's take a look at a couple examples. Our first example asks us to find the acceleration at time 3 given some position function h of t, which would correspond to, let's say, the height. So given the position function, we'll take one derivative, which gives us our velocity function, and we'll take one more derivative, which gives us our acceleration function. Now what we have to do is plug in our time 3 into our acceleration function. We get 6 times 3 minus 4, 18 minus 4, that's 14. Therefore, our acceleration at time 3 would equal 14. That looks pretty good. Let's try another example. In this example, we're given the velocity function v of t as 2t minus e to the t. And we're asked to find the position function s of t given some initial condition s of 0 equals 3. Recall that to go from position to velocity, we would take one derivative. So to go from velocity to our position, we would just integrate one time. Therefore, s of t, our position function, is equal to the integral of velocity 2t minus e to the t dt. Integrating 2t, we get t squared. Integrating e to the t, we also get e to the t, subtracting. And we also end up with a plus c. Now, to find the plus c, we use our initial condition. So our position at 0 would equal 0 squared minus e to the 0 plus c, and that should all also equal 3, given our initial condition. 0 squared is 0, e to the 0 is 1, we subtract 1, then we add our constant equal to 3. To solve for c, all we gotta do is add our 1 to the other side of the equation, we get c is 4. And therefore, our position function s of t would be t squared minus e to the t plus 4, given that our c value is 4. Hopefully with those two examples, we have a better understanding of how position, velocity, and acceleration relate to one another.